So far, we've looked at the roadmap of the AWS Developer Associate certification. Now it's time to start building the actual foundation. Think of AWS like constructing a modern city. Before you build applications, databases, or serverless architectures, you first need to know where your workloads live and who is allowed to access them. Those two ideas, infrastructure and identity, are at the heart of everything you'll build on AWS. By the end of this module, you'll understand how AWS is organized globally, how IAM makes security decisions, and why these concepts appear in almost every DVA-C02 exam scenario. Let's begin with the physical side of the cloud. Every complex AWS architecture starts with a surprisingly simple question: where will this application run? And immediately after that comes another question: who should be allowed to access it? Those two questions define this entire module. We're going to begin by understanding AWS's global infrastructure, regions, availability zones, and the decisions involved in selecting where workloads should live. Then we'll move into IAM, where you learn how AWS authenticates identities and evaluates permissions. Finally, we'll introduce EC2, the foundational compute service, along with security groups and storage options. These aren't isolated topics, they build on one another. If you don't understand IAM, serverless permissions later in the course will feel confusing. If you don't understand regions and availability zones, designing highly available architectures becomes much harder. So think of this module as pouring the concrete before building the house. Everything else in the course depends on these fundamentals. Imagine launching an online banking application. Before writing a single line of business logic, the engineering team decides which AWS region satisfies compliance requirement, which availability zones provide resilience, which engineers can deploy infrastructure, which application components are allowed to access databases. Those decisions happen before customers ever use the application. Cloud infrastructure and identity are the foundation of every AWS architecture. One of the biggest misconceptions about cloud computing is that the cloud is somewhere. In reality, the cloud exists inside thousands of physical buildings connected by high-speed networks. AWS simply manages that infrastructure for you. The hierarchy begins with a region, which is a geographic area containing multiple AWS data centers. Inside each region are availability zones, often called AZs. Each AZ is physically separated and has independent power and networking. That separation is intentional. If one availability zone experiences an outage, applications deployed across multiple AZs can continue operating. This is one of the core building blocks of high availability in AWS. Now notice another term on this slide: edge locations. These are different from regions and AZs. Edge locations are part of the CloudFront content delivery network. Their job isn't to run your applications. Their job is to cache and deliver content closer to end users, reducing latency. When choosing a region, think through four practical factors. First, compliance. Some organizations must keep data inside a specific country or geographic area. Second, latency. The closer your infrastructure is to your users, the faster requests travel. Third, service availability. Not every AWS service is available in every region. And finally, cost. Pricing varies between regions, and at scale, those differences can significantly affect your cloud bill. One detail worth remembering from the course material is that availability zone names, such as 1A, are account-specific labels rather than universal identifiers. Imagine you're building a healthcare platform serving German hospitals. Compliance may require keeping patient data in the EU. Latency favors hosting close to European users. Before deploying, you'd also verify that every AWS service your application needs is available in the selected region and compare regional pricing. Choose a region based on business requirements, not convenience. Knowing where your workloads run is only half the story. Next, we need to decide who is allowed to interact with them. Think of IAM as the security office for your AWS account. Every request to AWS passes through IAM before it reaches a service. IAM answers three simple questions: who is making the request? What are they trying to do? Are they allowed to do it? AWS gives us four building blocks. Users represent individual people who need long-term credentials. Groups allow us to assign permissions to multiple users at once. Roles are different. Instead of representing people, roles represent temporary identities that services, applications, or even other AWS accounts can assume. Finally, policies define permissions using JSON documents. Every request follows a consistent evaluation process. AWS authenticates the identity. It evaluates all applicable policies. If there's an explicit deny, access is denied immediately. If there's an allow and no deny, the request succeeds. If nothing matches, AWS applies an implicit deny. That default deny behavior is one of the reasons AWS IAM is considered secure by design. The goal is always least privilege. Grant only the permissions required for the task and nothing more. Suppose a developer only needs to upload files to one S3 bucket. Instead of granting full S3 administrator access, create a policy that allows uploads only to that bucket. Everything else remains denied automatically. IAM starts with no. Permissions must be explicitly granted. Understanding IAM concepts is important, but reading IAM policies correctly is what the exam tests most frequently. At first glance, IAM policies can look intimidating, but once you understand the structure, they are surprisingly logical. Every policy begins with a version field. In the supplied course material, this uses October 17th, 2012, which identifies the policy language version rather than the current date. Next comes the statement array. Think of each statement as an individual permission rule. The SID is simply a human-readable label. It doesn't affect the decision. The effect field tells AWS whether the rule allows or denies the request. Then comes action. Actions combine a service name with an operation. For example, S3:getObject. Resource specifies exactly which AWS resource the rule applies to. Finally, condition narrows the rule even further. For example, a policy might allow access only from a trusted office IP address. Here's the evaluation order you should always remember. First, AWS looks for an explicit deny. If one exists, the request stops immediately. If there isn't an explicit deny, AWS searches for an allow. If no matching allow exists, the request is denied by default. Notice that security comes from specificity. The more precisely you define actions, resources, and conditions, the safer your IAM policies become. Instead of allowing access to every S3 bucket in an account, create a policy that allows only read objects from one application bucket and only from trusted corporate IP addresses. That's the principle of least privilege in action. Read IAM policies the same way AWS evaluates them. Deny to allow to implicit deny. Now that you understand permissions, the next question becomes, how should workloads authenticate without exposing long-term credentials? That's exactly what we'll cover next with IAM roles and credential hygiene. Quick recap. In this lesson, we established four critical AWS fundamentals: the AWS Global Infrastructure Hierarchy, regions, availability zones, and edge location. How to choose a region using compliance, latency, service availability, and cost. IAM building blocks, users, groups, roles, and policies. How AWS evaluates IAM policies using explicit deny, allow, and implicit deny. These concepts form the security and infrastructure foundation for everything you'll build later in the course. Next, slides, where we'll cover IAM roles and credential hygiene, EC2 fundamentals, security groups, EC2 storage, EBS, EFS, instance store, and AMS. These topics continue directly from this lesson and complete Module 1's foundational concepts. Now that we understand how AWS evaluates permissions, there's another critical question every cloud engineer must answer. How should applications authenticate to AWS? Should we embed access keys in code, or is there a better, more secure approach? This is where many real-world security incidents begin, and where AWS IAM roles become one of the most important services you'll ever learn. One of the fastest ways to compromise an AWS account is by exposing long-term access keys. Developers accidentally commit them to Git repositories. They appear in screenshots. Sometimes they're copied into configuration files or shared through chat applications. That's exactly why AWS recommends using IAM roles whenever possible. Let's compare users and roles. A user is designed for people. Users typically have long-term credentials, such as passwords and access keys. A role is completely different. A role has no permanent credentials. Instead, something temporarily assumes that role. When that happens, AWS Security Token Service, STS, issues short-lived credentials that automatically expire. This dramatically reduces the risk associated with leaked credentials. The course also highlights 6 credential hygiene habits that every AWS developer should follow. Enable MFA for the root account and privileged users. Avoid using the root account for everyday work. Never store access keys in source code. Attach IAM roles to workloads such as EC2 and Lambda. Rotate and remove any long-term keys that must exist. Regularly review your environment using tools like the Credential Report and Access Analyzer. Now look at the Lambda example. When a Lambda function starts, it automatically assumes its execution role. STS provides temporary credentials. The AWS SDK retrieves those credentials automatically. That means your application code doesn't need hard-coded secrets. The credentials are temporary, managed by AWS, and disappear when they expire. This is one of the biggest mindset shifts for developers moving to AWS. Instead of managing secrets yourself, let AWS manage identities securely. Imagine a Node.js application running inside Lambda. Instead of storing AWS credentials in environment variables, you simply assign an execution role that allows reading from DynamoDB. The SDK automatically authenticates using temporary credentials. No secret keys, no credential rotation in code. Workloads should authenticate using IAM roles, not long-term access keys. Now that we know how identities authenticate securely, let's move to the compute service that powers millions of AWS applications, Amazon EC2. Amazon EC2 is one of the oldest and most widely used AWS services. Think of it as renting a virtual server in the cloud. Unlike serverless services, EC2 gives you complete control over the operating system, installed software, runtime environment, and application. But that flexibility comes with responsibility. The course introduces an important concept. AWS manages the infrastructure below the operating system. You manage everything above it. That includes operating system updates, installed packages, application code, runtime configuration, firewall rules, and your data. Next, let's decode EC2 instance names. Take m5.large as an example. The first letter identifies the instance family. The number indicates the hardware generation, and the final portion describes the instance size. Once you recognize this naming pattern, instance names become much easier to understand. The presentation groups instance families into common categories: general purpose for balanced workloads, compute optimized for CPU-intensive tasks, memory optimized for applications needing large RAM, storage optimized for high-performance local storage. Finally, let's discuss pricing. AWS offers multiple purchasing models. On-demand provides maximum flexibility. Reserved options reward long-term commitments. Savings plans offer flexibility across compute services. Spot instances can reduce costs dramatically but may be interrupted. Dedicated hosts exist for specialized compliance or licensing requirements. The key idea isn't memorizing percentages. It's understanding the trade-off between flexibility, commitment, and interruption risk. A startup launching a new product might begin with on-demand instances because traffic is unpredictable. Once usage stabilizes, moving to reserved pricing or savings plans can reduce long-term costs. Batch video processing jobs that can tolerate interruptions may be excellent candidates for spot instances. EC2 gives you maximum flexibility, but also maximum operational responsibility. Running servers is only one part of infrastructure. The next question is, how do we control network traffic securely? One of the easiest ways to understand security groups is to think of them as virtual firewalls attached directly to your EC2 instances. Every packet entering or leaving an instance passes through these rules. The course emphasizes 5 ideas that matter most. First, security groups are allow only. You can't create deny rules. Anything not explicitly allowed is denied. Second, inbound and outbound traffic are evaluated separately. Third, and this is extremely important, security groups are stateful. If inbound traffic is allowed, the return traffic is automatically permitted. You don't need to create additional rules for response packets. Fourth, security groups can reference other security groups instead of individual IP addresses. This makes architectures much easier to manage because the rules automatically apply as your fleet scales. Finally, changes take effect immediately without restarting the instance because security groups are attached to the Elastic Network interface. The slide also presents the classic three-tier architecture. The web layer accepts HTTPS traffic from the internet. The application layer only accepts traffic from the web layer. The database only accepts traffic from the application layer. Notice that the database never communicates directly with the public internet. This layered approach dramatically improves security. Imagine a production e-commerce application. Customers connect only to the web servers. The web servers communicate with application servers. Application servers communicate with the database. Each security group trusts only the layer immediately before it. Reference security groups, not IP addresses for scalable architectures. We've secured our compute resources. Now let's decide where their data should actually live. Storage decisions become much easier when you ask two simple questions. Does the data need to survive the instance? And does more than one instance need to access it? Those questions naturally lead to the four storage options presented in the course. First, EBS. Think of it as a persistent hard drive attached to a virtual machine. It survives instance stops and can be detached and attached to another compatible instance within the same availability zone. Next is instance store. This is physically attached storage that offers extremely high performance. The trade-off is durability. When the instance stops or terminates, the data is lost. It's ideal for temporary caches, scratch space, or buffers, but never for important business data. Then we have EFS. Unlike EBS, EFS is a shared network file system. Multiple Linux instances can mount it simultaneously, making it a strong choice for shared application files. Finally, the presentation introduces Amazon Machine Images, AMIs. An AMI isn't simply storage. It's a reusable template containing the operating system, software configuration, and launch settings needed to create new EC2 instances. The slide also compares two EBS volume families. GP3 is presented as the default choice for most workloads. IO2 targets latency-sensitive, high-performance database workloads. The key isn't memorizing every storage type, it's understanding which problem each one solves. Suppose you're deploying a WordPress application. The EC2 instance boots from an AMI. The operating system resides on an EBS volume. Uploaded media files shared across multiple web servers could live on EFS. Temporary rendering files might use Instant Store. Each storage option solves a different architectural requirement. Choose storage based on persistence and sharing requirements, not simply performance. With compute, storage, networking, and IAM foundations now in place, we are ready to begin building larger AWS architectures in the next module. Quick recap. Today, we've completed the core foundations every AWS developer needs. Secure authentication with IAM roles and temporary credentials, Amazon EC2 and the shared responsibility model, security groups for network level protection, EC2 storage options, and how to choose between them. These four concepts appear repeatedly throughout the DVA-C02 exam and form the foundation for serverless, containers, databases, and networking later in the course.